Okay. Yeah, we've talked about the integral now, started talking about it. And we know by definition the integral from a to b is f of x dx. It's the limit as n goes to infinity of these areas of these rectangles. Yeah, this is the sum of the rectangles. Our height is the function value at each point. Delta x is the width. We add those all up, and then what does this do? What does the limit as n goes to infinity do? Well, it makes, we started with 4 rectangles, and we go to 10 rectangles, we go to 50 rectangles, because the more rectangles you get, the better. And this is the ultimate, because what does this do for us? This makes it infinitely many rectangles, and so we're running our rectangle numbers to infinity. And so it matches exactly up to this area, which, again, we said the area under the curve is also known as this integral from a to b, one way we can interpret it. Okay, well, another thing they reference, I don't think I've had you do them yet, but now what we're saying is our computations that we've been doing, those are approximations to this integral. And one other term that we might encounter, you might see, is what's known as the midpoint rule for integrals. And that is this. If you want the integral from a to b of f of x dx, that's approximately equal to the sum I equals 1 to n, how many ever rectangles you want. And if we're using a midpoint, then our sample point are the midpoints. And the notation, I think I discussed that with you, the notation for midpoint is the bar. So that's what we sometimes refer to as midpoint rule. So it's the midpoint rule is just using the Riemann sums and the midpoints as your sample points. Okay. So let's try one here. All right, so let's use the midpoint rule. With n equals 5 to approximate the integral from 1 to 2 of 1 over x dx. Well, this is, again, we're kind of stuck in sort of a rut here. We'll get out of it today, but doing the same thing. I'm just going to approximate this integral because this integral is the area under the curve from 1 to 2 with the rectangles. And midpoint rule just says use midpoints. All right, so let's start with delta x here. Delta x is, what would delta x be here? Delta x would be b minus a over n. That's what delta x is. So in this case, what's my b and a? Well, a and b, right? This is a, that's b. If we're talking about the integral, yeah, it's just the endpoints. So I'm going from 1 to 2, so it's 2 minus 1. They tell me n is 5, so divide that by 5, you get 1/5, which is 0.2. Okay, so if I think about then this integral I'm estimating here, 1 over x looks like this. So I'm just going from 1 to 2, And I'm dividing up that into 5 pieces, so what's my x1 here? Well, x1, the first right endpoint would be 1 plus delta x, right? 1.2. And then x2 would be 1.4. Yeah, you just add 1.6, 1.8, and then finally x5 is 2.0. Right? So I'm just increments of 0.2. But since I'm using the midpoint rule, I also need x1 bar, the midpoints. Because that's going to be, that's what I'm going to plug in. The midpoint is what I'm going to plug into my function. So what's the first midpoint? Well, the first midpoint would be halfway between 1 and 1.2, wouldn't it? 1.1? X sub 2 bar would be 1.3 then. X sub 3 bar is 1.5, so on and so forth. Okay, so my integral then by midpoint rule from 1 to 2 of 1 over x dx, well, this one's pretty easy to compute here. It's approximately equal to then, what would I have? I'd have the first one would be a 0.2 by, the height would be f of x, which is, f of x is the 1 over x. So it'd be 1, let's write that way. F of 1.1, wouldn't it? Because I'm looking not at the right endpoint, not the left endpoint, I'm looking at the midpoint. So my height's going to be the function value at 1.1, which is 1 divided by 1.1. Okay? 0.2 then. The second rectangle, well, I'm going from 1.2 to 1.4, but I'm using the midpoint as my height, or f of the midpoint. So it'd be f of 1.3, and then f of 1.5 times 0.2, and then the same for the fourth one, f of 1.7 at the midpoint, and then the last one would be 0.2 wide, and then the height would be f of 1.9. Plug that into your calculators or however you want to do it. But this one's a fairly easy function, so you can just do, this would be 1 divided by 1.1. This would be 0.2 times 1 divided by 1.3. 1 divided by 1.5, and so on. So it's kind of a wash, I would think, on which one would be easiest. Does that make sense? All right, has anybody got it yet? Okay. Check you on that. Not that I don't trust you. Yeah, this one's pretty easy to. Uh-oh. Okay. I think I got it. 0.6919? Is that what you said? 0.6919 is right. Okay? All right. So that's the first thing. Second thing, any questions on that? Further discussion? Like I said, that's really something we've already talked about several times now. We're just calling it now the midpoint rule. So that's what it wants you to do. That's all it means. Riemann sums the rectangles with midpoints. Okay? All right, well, let's also talk here about a few properties of integrals. First of all, knowing knowing that, when I'm talking about the integral from a to b of f of x dx, that means, if you got your function here, a to b like that, the integral is that, right? Or the net area under the curve if it drops below the x-axis. With that in mind, then, what do you think this would be? Let's call it property 1. The integral from a to a of f of x dx, or b to b, or whatever. Area under the point A, what would be the area under a point, a value, like A? Is there any area? No. That's just there's no area because you don't go anywhere. Yeah, that's, if your limits are the same, the integral is 0. I mean, that won't happen just a whole lot, but yeah, there's no area from A to A there. You have to have some width to have any area at all. Property number 2. You know, we're talking A to B here. What if I reverse that? How would that be related? So instead of the upper limit being B, like normal, we're saying the upper limit's A and reversing it down on the lower limit too. So essentially, instead of going A to B, this is saying go B to A, right? The lower limit's B. So how would that compare? Well, if you think about it, think about delta x. You know, it all gets back to the limit definition. And delta x, remember delta x is b minus a over n. Well, if I switched b and a there, don't I get a minus b over n? Which isn't it the negative of b minus a over n? Yeah. What changes is this delta x is now a negative. Instead of delta x being a positive, comparatively so, you know. Yeah, that's what happens. If you run it backwards, you get the opposite sign of what it was originally. Now, if this was originally a negative, then this will be a positive. If this is originally a positive, then this will be a negative, is what we're saying. Okay? So reversing it, if we went A to B gives us a positive, then this would give us a negative. Because we're going backwards, so to speak. So if you reverse it...
And that negative area doesn't necessarily equate to below the x-axis.
No, as a matter of fact, it would be exactly the opposite. Above the x-axis would be negative if we go this way, and below the x-axis would be positive, right? Because they're the opposite signs. So anyway, just a few things to think about. Now, some other pretty useful ones. Those, like I said, those may not happen a whole lot, but just in case. Yeah, property 3 is a useful one. And it says if you have two functions added, and you know, adding and subtracting are pretty well synonymous. The good news is, yeah, you just have to do those individually. You can just think of, if you're doing the integral of an f of x plus g of x, so two things like an x squared plus an x cubed, yeah, you just have to do the integral of f of x plus the integral of g of x if it's added. They're added. Doesn't quite work so well if it's a multiply. Adding and subtracting. Yeah, so we could throw in the minus there. But yeah, I should point out, and that that gets back to the limit definition. Again, that's we'll talk more about this in just a second. But again, the limit definition says this integral really is the infinite limit of these rectangles, these summations of these rectangles. Well, if my function is actually f of x plus g of x, well, f of x plus g of x, the sum of, we'll talk about this more in just a second. Yeah, the sum of f of x plus g of x does equal the sum of f of x plus the sum of g of x, right? I mean, it's all sums. So you can break it up however you want to. That's what you're going to get, okay? Now, very important there, and it's subtraction the same way because they're all added. We're just talking adding things together. Break it up however you want to. Add these together first, then add those in. Doesn't matter. Add them together at the same time. Whatever. But it is important to note here that the same can't be true, said to be true of this. And I'll probably show you one more like this later on. Yeah. If two functions are multiplied together, you can't do the integral of the one times the integral of the other. It only works for adding or subtracting. Doesn't work for multiplication. Throw in division right there too. It doesn't work for division. So, but we'll talk more about that in a second. Okay. A couple more of these and I'll go on to something else here. So number 4, yeah. Turns out, we'll say more about a lot of this stuff in just a second, but yeah, if you have c times f of x, a constant, or c is just standing for a number, usually, yeah, that c can be pulled out. And just do the integral of f of x times the c. Pretty straightforward one. And then number 5 is one we'll use a little bit later. Say we're going a to c, f of x dx. I think, let me go use the same notation as the book. If we're going integral a to b f of x, sometimes it makes sense to divide the integral up into two pieces where, we're talking about a to b here. And let me do one where this is actually how we'll really more use it. Say we've got a corner something like that from A to B. Well, we know something funny is happening here at this corner. Call it at C. So it makes more sense when you have a corner like this or something like that, something fishy going on at some point in there in your graph, it makes sense to do two integrals. And property 5 that I have up here says you can do that. It says, yeah, I can break up from A to B. I can go from A to C, f of x dx, and then add that to C to B, f of x. See what I'm saying? You can do that with integrals. Okay? So see what we did? We broke it up into two separate integrals, where C is this point in the middle, or somewhere in between A and B. Okay? You can do that. All right. So those are, some few properties of integrals. All right. Did y'all get that last one? I erased that pretty quickly. Did everybody get this last one? Everybody still writing on that one? I erased it pretty quick. the integral number 5, a to b f of x. That's what it was. Okay. All right. But here's last thing let me mention on 5.2, then we'll go to 5.3. That is this. If, say, I want to write the integral 0 to 5 of sine of x dx using the definition of the integral. What would that look like? Using that definition of integral, what would the integral 0 to 5 sine of x dx look like? Well, you can take it a lot of ways, and we're going to take my next one, my next example with the integrals anyway, all the way through. But I was trying to see, yeah, definition 2, I guess it is. Well, that's just using the limit definition, the limit of the summation. That's all basically one here, or what I'm wanting right now anyway. Okay, well, to write it this way, what would this be? F of xi star, what is that going to look like? Where's our f of x? What's f of x in this case? Sine of x. Sine of x is my function, so this will be the limit as n goes to infinity. Sum of, and I'll go ahead and put my I equals 1 to n, I forgot that. Yeah, f of x sub I star would be, well, to plug in, since I don't say left, right, midpoints, or whatever, it's just sine of x sub I star is what that would be, right? I don't know what I'm going to plug in, but it's going to be sine of whatever I want to plug in. Now, the other thing we could go ahead and do, what's my delta x? Well, delta x we know is b minus a over n, but what's my b and a here? 5 and 0. So what is b minus a over n going to be? Well, I know it's 5 for b, 0 for a. Now the n is varying, so it's still n. So one way, and like I said, we can take it further, and we'll do that more in just a second. But anyway, there is a definition of the of the definite integral, and if we use the definition, here's for this one anyway, kind of what it looks like at up to a point. We can take it further, but for now, okay. So there are things that we plug into. Any question, concerns, and then we'll start 5.3 here.